Hello student, I am Vishwanath. Welcome to my YouTube channel. Today I am going to discuss about the torque acts on a loop, current carrying loop placed in a uniform magnetic field. Let ABCD is a current carrying rectangular loop. The length of AB or CD is small l and the width or breadth of the rectangle BC and ABC or AD is small b. That is, AB is equal to small l and BC is equal to small b. Capital B be the uniform magnetic field. Here capital N is the normal vector drawn to the plane of the rectangle ABCD. That is, N is normal on the plane of the rectangle ABCD. The angle between N vector and B vector is theta. Angle between N vector and B vector is theta. This is the angle between N and B. I amount of current is passing through the rectangular coil. Now, these four arms act four forces. This forearm can experience four forces. AD experience F1 force, BC experience F2 force, AB experiences F3 force and CD experiences F4 force. Now F1, the force F1 and F2 are equal in magnitude but opposite in direction. That is, F1 is equal to minus of F2 and they act along the same line. Okay, that's why their resultant is 0 and they do not form any couple. That's why the F1 and F2, the two forces F1 and F2 do not influence the motion of the coil. Okay, now F1 and F3 and F4, the magnitude of F3 and F4 are same. This is equal to BIL. Okay, here B is the magnitude of the magnetic field, I is the current and L is the length of AB or CD. Now the direction of F3 is perpendicular to the paper, or direction of F3 is perpendicular to AB and perpendicular to the magnetic field B, and it comes out from the normal to the paper towards you. Okay, and the direction of F4 is also normal to the capital B vector and normal to BC, and it moves towards the normal to the plane of the paper, inward direction to the plane of the paper. That's why you can say that F3 and F4 are same in magnitude but opposite in direction, and they do not act at the same line or same point. That's why they form a couple. That is, F3 and F4 forms a couple. Therefore, this rectangular loop experiences a torque due to this couple. Okay, and we can denote the torque is tau vector by the tau vector. Now you know that the magnitude of torque is equal to force into the normal distance between the two forces. That is the normal distance between F3 and F4. Here the normal distance between F3 and F4 is B sin theta. That's why you can write that the magnitude of torque tau is equal to magnitude of F3 force or maybe F4 magnitude of F4 force into B sin theta. Now putting the value of magnitude of F3, you get magnitude of torque is equal to BIL B sin theta. Okay, here L into B is equal to capital A, is the area of the loop, and capital A vector is the area vector of this loop. And you know that area vector is acts always in normal direction to the surface area. That's why the area vector A is parallel to n vector, capital N vector, and the angle between area vector A and capital B vector is also theta. That's why you can write that tau vector is equal to I into capital A vector cross capital B vector. This is the vector form of the couple or tau. Now, for the n number of turns of the loop, you can write that torque tau is equal to Ni into capital A vector cross capital B vector. Here, n is the number of turns of the coil. Okay. Next topic is moving coil galvanometer. Here, a rectangular coil ABCD is placed in a uniform magnetic field. In this case, the area vector capital A and the magnetic field vector capital B are mutually perpendicular to each other. In this coil, moving coil, this rectangular coil is suspended from a rigid, non-flexible wire, and this wire conducts a current I, which is connected to a battery. Okay, and this coil is also placed on a spring, metallic spring. This is the circuit, closed circuit, and a small mirror is also attached. A small mirror is also attached to the string of the coil, from which the coil is suspended. Okay, this is the string by which the coil is suspended. Okay, and a small mirror is attached with this string. We can denote the small mirror by capital M. Capital I amount of current is passing through the coil. Due to the current passes through the coil experiences a torque, and due to this torque, the coil deflected by an angle theta. You know that tau is equal to C into theta. Here C is the torsional rigidity of the wire, torsional rigidity of this wire. Okay, from which the coil is suspended. You also know that torque tau is equal to BINA. That means BINA is equal to C into theta, BINA. Here another scale is placed parallel to the plane of the coil, and a light ray is incident normal to the mirror. Okay, when the coil is at rest, then the reflected light ray falls on the midpoint of the scale. Okay, and this scale is pointed as 0 at the midpoint, and 1, 2, 3 centimeter and millimeter scale, and at the right side of the midpoint and also left side at the midpoint. Clear? When the coil is deflected by an angle theta, then the reflected ray also deflected by the angle 2 theta. Clear? 2 theta. That is the due to the angular deviation of the rectangular coil theta, the angular deviation of reflected ray is 2 theta. Here capital D is the distance between the mirror and the scale. Here small capital D is the distance between the mirror and the scale. Due to the angular deviation of the reflected ray, which is measured from the scale, we can measure the current by the following formula. Here small d is the angular deviation or displacement of the reflected light ray on the scale. Okay, that is when the coil is deviated by an angle theta, then the reflected ray also deviated. That is, in this case the reflected ray do not fall at the midpoint, it deviates at somewhere and another point on the scale. Okay, and the deviation is small d, and you know that small d is proportional to theta. Okay, that's why we can write that I is directly proportional to small t. Therefore, I is equal to k into small t. Here, k is a constant. It is equal to c by 2nBAD. 2nBAD. At first, by sending a known current I and measuring the linear deviation or linear displacement of reflected ray, that is, we know knowing the value of I and measuring the value of small d, we can easily find out the value of k. Then in the next case, by knowing the value of constant k, we can measure the unknown current I by measuring the value of small d. This is the working principle of moving coil galvanometer. By this galvanometer, we can measure very small amount of current. Okay. By the tangent law, we can easily prove that theta is equal to small d by 2 capital T. Therefore, we can write the value of k is equal to c by 2nBA capital T. Now, current sensitivity and voltage sensitivity of this moving coil galvanometer. What is sensitivity of an instrument? Sensitivity of an instrument denotes the accuracy of the measurement of that instrument. That is, due to the increase of the sensitivity of the moving coil galvanometer, we can measure very small amount of current and very small amount of voltage and very small amount of difference of the current and very small amount of difference of the voltage. And sensitivity of the moving coil galvanometer can be expressed as theta by I. Okay, this is equal to NBA by C. From the previous relation, we can write that theta by I is equal to NBA by C. And you know V is equal to I into R. That's why the voltage sensitivity is equal to theta by V is equal to NBA by CR. Here R is the resistance of the galvanometer. Therefore, to increase the sensitivity of the moving coil galvanometer, we have to increase the number of turns, that is capital N. We have to increase the intensity of magnetic field, B, capital B, and the area of cross section of the coil, and to decrease the torsional rigidity of the wire from which the coil is suspended. Okay, due to the increase of the magnetic field capital B, this coil is placed between the two strong magnets. Okay, and these magnets are curved. That's why the maximum lines of force of the magnetic field can be passes through the coil. Okay, that is the area of cross section of two magnets is not flat, it is curved. Okay, uh, this is the actual structure of the two magnetic poles of the two magnets. They are powerful magnet, and due to the curving of the poles of these two magnets, the maximum lines of force can passes through the coil. That's why the intensity of magnetic field, that is capital B, also increased. Thank you for watching my video. Have a nice day. Meet you again.